buildings in my place has its own street.
Oh.
So we're not right on 62nd Street, but everybody's like, I'm in 134 62nd Street.
Okay, yeah.
The office is on 20. So I said,
See, we're all in one big, it's just 2,800.
yeah.
Okay, let's begin, everyone. I have posted meeting 19 extra related to section 7B, and that's getting into exciting a linear second order ODE with polynomials. Okay. And so, as you know, there are two parts in solving linear second order ODEs, right? The first part is to find the homogeneous solution, and the second part is to find the particular solution. Now, the homogeneous solution is something that had been reviewed since the beginning of the semester, and now you are looking for the particular solution when the right-hand side is excited by polynomials, and this is has a very deep consequence in the sense that when you have arbitrary functions, you can expand into Taylor series, right? I have mentioned to you, or in general power series. Okay, so exciting by polynomials is part of solving that, and just to motivate you further, because students tend to be more motivated when we talk about exam. So, so this is directly related to problem 2 of exam 1.1. Okay, so please take a look at this. All right, and as you know, I have continuously updating the slides, the topics that we covered, and this is for a quick review. I mean, a quick refreshing of your mind. We have considered or reviewed quickly the orthogonality of the eigenvectors for the standard eigenvalue problem, right? Because once you understand the concepts of the standard eigenvalue problem, you can generalize these concepts to generalized eigenvalue problem. Okay, so for the standard eigenvalue problem, the mass matrix is an identity matrix, and you have the regular dot product. Okay? And you know how to compute the length of the eigenvectors is just by doing the dot product, or you can do phi transpose times phi. Okay, it's the same thing. And then you know how to normalize the eigenvectors. So this is all well known a long time ago. But what is new is the generalized eigenvalue problem, where the orthogonality of the eigenvectors would be with respect to a non-identity mass matrix. Okay, so the mass matrix is in general not an identity matrix, and you can introduce new concepts like modal masses, and modal masses is a generalization of the square of the length of an eigenvector, right? Because when you do the dot product in the standard eigenvalue problem, you have the square of the length of an eigenvector. So that is generalized to what is known as the modal masses. And then you can also normalize the eigenvectors with respect to the modal masses. Okay, essentially take the square root of the modal masses, right? And you are also introduced to the Kronecker delta, which is a very powerful way to write the orthogonality in compact form. Okay. And I have built the animation of the vibration mode 1 and mode 2. Mode 1 is in phase, and mode 2 is out of phase. 180 degrees out of phase, just by using trigonometry. Okay, so that's a quick refreshing of your mind there. And as always, I have annotated my handwritten notes after class. So if you click into this link to meeting 18 last time, that you would see, you would see my annotated handwritten notes from last time with a lot of annotation here. And so this was what I just reviewed, right? The use of the Kronecker delta to compactly representing 4 different relations into a single compact relation. Very beautiful, very elegant. And if you go to graduate school, this is very important. Okay. So I think we continue on with this from here. And my goal for today, section 7b, I did mention to you, I didn't show this, but this is, you can see here the search for the particular solution under polynomial excitation. Okay, so this is a polynomial here, and this is the expression for the particular solution. All right, and that's in the extra extra meeting 19. All right. So my goal for today is to wrap up section 53D. Okay, we just have a little left, and I will go directly to section 53E. And the goal of section 53E is uncoupling. Okay, that's the final goal of section 53E. Why do you need to uncouple the two coupled equation of motion? Can someone remind the class quickly? Why do you need to uncouple the equation of motion? Deep learning credit, Anderson?
Otherwise you can't solve it.
Yeah. If the two differential equations are coupled, you don't know how to solve it. But you know how to solve uncoupled scalar second order ODEs, right? And that have been reviewed since the beginning of the semester. All right. Okay. So let's move quickly to reach this goal. And this is just meeting 18, as you already saw. So let me bring up section 53 D and then E. Okay. So we just have a little left from section 53D. So let's finish that up at the end. So the animation is done. I have done this part where you would put this. I can just draw your attention to this matrix, big phi bar, where you put over here the eigenvector phi 1 bar and here phi 2 bar. Okay. The over bar just designate that these eigenvectors have been normalized with respect to the mass. All right. Okay, recall that the normalization factor was 1 over square root of 5 and square root of 3 over 10 for these eigenvectors respectively. Okay. So let's move forward. So once you introduce this matrix cap phi bar, which is the normalized counterpart of the matrix cap phi you saw before, then you can write the orthogonality of the eigenvectors in this matrix form. Now these are matrices. Okay, cap phi bar transpose times the mass matrix times cap phi bar equal to the identity matrix. This is a 2 by 2 identity matrix. Okay. All of these matrices are 2 by 2. So and the orthogonality, when you expand this compact matrix expression in terms of matrix variable into more into the coefficients. Okay, so phi gap phi bar transpose is this matrix here, which I just reviewed for you. As you know, gap phi bar is the matrix that has the two eigenvectors arranged side by side, and this is just a mass matrix in between. And recall that this matrix here is the gap phi bar matrix, right? With two eigenvectors side by side. We have phi 1 bar and phi 2 bar. This is the mass matrix here. And this matrix here is the transpose of the gap phi bar matrix. Okay, so there's a sign transpose there. And if you work out the details, and please do that as an exercise, you should find an identity matrix, okay, which confirm the matrix relation of that. Okay. If you have any questions, please do ask. And now let me motivate you why you want to normalize the eigenvectors with respect to the mass, is so that when you uncouple the equation of motion, the coefficient for the acceleration would be 1. Okay, the coefficients for the acceleration would be 1, and that is called the standard form of second order differential equation. Make it a little simpler to solve. All right. For those of you who are not familiar of what it means by standard form of the second order differential equation, then you can review section 1 to section 6 there in the extra lectures. Okay. So now let's move forward to section 53E, and let me do the following. Let me have two small windows side by side so that I can give you the big picture. Okay. So this is section 53E here. Right. And so we already saw orthogonality with respect to the mass matrix. And let me show you the end result. Okay, the end result, skipping through a lot of concepts that we will do. The end result is the following. And it is written here. Right here, you see. So this is two linear second order differential equation, completely uncoupled. You know, the index I goes from 1 to 2, and the coefficient of yi double prime is equal to 1. Okay, so let me use a middle window, and so I can zoom in. Yeah. All right. So this is the end goal. Okay. So this is what we want to achieve. These are two linear second order differential equations, right? I equal to 1 or 2, and in one equation you have only either y1 or y2. Okay. So there's no coupling here. So it's completely uncoupled. And keep in mind the coefficient of the acceleration is 1 for each of the modal equations. This is called the modal equation. There are two modal equations. All right, so that's what we want to achieve here. So let's let's go back. And let me use this side here. Okay, so where do we begin? We begin with stiffness orthogonality. Okay, you have mass orthogonality. Now we talk about stiffness orthogonality of the eigenvectors, that is. So let's go up. Let me zoom out so you see how I navigate. I just go up to the top. Okay, stiffness orthogonality. All right. So what does it mean? It means the following. It is just a consequence of the mass orthogonality. Okay, let me do the following. Let's recall that you have. This is the generalized eigenvalue problem, Maria.
You said the stiffness orthogonality is a result of.
Consequence of the
Is it
mass
consequence?
orthogonality, and I will show it now.
Okay.
Yes.
All right. I was going to be like,
Yes.
what do you mean by that?
Yes. So this is generalized eigenvalue problem. Everyone knows by now. We already found two eigenpairs, right? The eigenvalue and associated eigenvectors. So the index J is equal to 1 or 2. Okay. Now this is in general where you have n degrees of freedom, but in this at this level we just deal with 2 degrees of freedom. That's complex enough at this level, right? So you can think of n here. This n here is equal to 2. Okay. And we call that the eigenvalues beta j is equal to the square of the circular frequency. So beta j is the square of omega j. All right. So this is nothing but a rewriting of the generalized eigenvalue problem. Now this is new. Okay. Pre-multiply throughout on both sides by phi transpose. Okay. You see, that's why when I wrote the equation above, I used j. But when I pre-multiply, I use the index I. So phi bar I times k times phi bar j, you can guess, right? I mean, you can remember the chronicle delta, and we'll get there. So phi bar I transpose times the stiffness matrix times the normalized eigenvector phi bar j equal to omega j square, because omega j square is beta j, right? And on the left-hand side, you have you have mass times phi bar j, and then multiply by phi I bar transpose in front. That's pre-multiply. Then you see now you use the result that you obtained before. That is the mass orthogonality. The mass orthogonality of the eigenvectors tells you that phi I bar transpose times mass times phi j bar is delta ij. So that's it. Now you have shown that the eigenvectors are also orthogonal with respect to the stiffness matrix, but it's not normalized with respect to the stiffness matrix because these coefficients are not equal to 1. If this coefficient is equal to 1, then the eigenvectors would be orthogonal with respect to the stiffness matrix. But because these coefficients here, the square, these are actually the eigenvalues here, not equal to 1 in general. So you say that the eigenvectors are orthogonal with respect to the mass matrix, but not with respect to the stiffness matrix. They're still orthogonal in the sense that, let me restate as follows. The normalized eigenvectors are normalized with respect to the mass matrix. They are orthogonal with respect to the mass matrix. And the phi bar, the normalized eigenvectors, are normalized with respect to the mass matrix. Now, the eigenvectors are orthogonal to both the mass matrix as well as to the stiffness matrix. But the normalized eigenvectors are not normalized with respect to the stiffness matrix. They are only normalized with respect to the mass matrix. Okay? Clear to everyone? Normalization is only done with respect to the mass matrix. But orthogonality is with respect to both stiffness, mass and stiffness matrices. Orthogonality is very important because that would lead you to diagonal matrices. Okay? And diagonal matrices, could someone remind the class why do we want diagonal matrices and get active learning credit? Diagonal matrices is very important, right? Remember at the beginning, the stiffness matrix is not diagonal. The stiffness matrix is a full 2x2 matrix, right? So why do you want to have diagonal matrices?
That's uncoupling, right?
Uncoupling, yeah. The mass matrix is already diagonal, but the stiffness matrix is not. So that's why the two equations of motions are coupled. And you use the eigenvalue problem to diagonalize the stiffness matrix. And in doing so, you uncouple the two equations of motion, just like in the static case. Okay? So Kevin. Fine. So that's the goal of all of these, work. And so recall again the matrix gap phi bar with the two columns being the two normalized eigenvectors with respect to the mass matrix. Okay. Pay attention to the words, the terminology that I use, because these are very descriptive. Okay, so let me go up here. And so what happened to the stiffness matrix when you multiply the matrix gap phi bar transpose times K times gap phi bar? Remember, gap phi bar is the matrix with two eigenvectors side by side. Well, you get this diagonal matrix. So this is a realization or diagonalization of the stiffness matrix here, right? So you have a diagonal matrix, and on the diagonal, the coefficients are essentially the eigenvalues, right? 4 and 9, that's beta 1 and beta 2. And just to introduce a notation that you would see used later, I call B1 and B2, but I could also write beta 1 and beta 2 there. Okay. All right. And this is the a matrix which I call defined as gap omega, and gap omega does not have the square, right? So this is gap omega square. You have omega 1 and omega 2, and these are the circular frequency, vibration circular frequency. You can verify that if you take a diagonal matrix, multiply by itself, then the diagonal coefficients would be squared. Okay. So take this matrix, multiply by itself, you should get this one. Right. So in other words, the matrix gap omega is the square root of this diagonal matrix. Okay. All right. So then the next step is to verify in terms of plug in the numbers, right? So again, once more, let me see whether I can zoom out so you have, that's a little far, but I think you can get it. Again, phi bar is this matrix here, which is the matrix that has two eigenvectors side by side, and that's this matrix, right? And recall that this is phi 1 bar, and this is phi 2 bar. Okay. The stiffness matrix goes here, and this is the stiffness matrix, right? Of the spring mass damper system, and then the transpose is just this one, okay? And that's the transpose of the matrix gap phi bar, and when you work out the algebra, you should verify that you get a diagonal matrix with the diagonal coefficients being the eigenvalues, right? Beta 1 and beta 2, 4 and 9. Here I call B1 and B2 just to show you that you would recover, but I could have used the notation beta 1 and beta 2 as well. When I update my notes, if I remember, I would change to beta 1 and beta 2. Oh, maybe not, because I think now I remember there's another reason why I use this when we get to the modal equation. It would look similar to what you see in the theory of the scalar differential equation. So keep in mind, I think I must have defined somewhere up here that B is the same as beta. I think I may written it somewhere. But anyway, you can think of B1 is the same as beta 1, okay? And B2 is the same as beta 2. And the notation B is very useful to connect you to the theory of scalar second order differential equation. Yeah, that's why. Yeah, that was really the motivation to change. Okay, now the damping matrix. Okay, so here we do similar similar operation, and this operation called projection. Okay, you project the matrix, the damping matrix, on the basis of the normalized eigenvectors. So phi bar transpose times the damping matrix times phi bar is, again, let me zoom in so you have a bigger. Okay, so if you replace phi bar transpose times the damping matrix C with all the coefficients, numerical coefficients, and this is phi bar, then you would obtain a diagonal matrix, and I give the symbol A1 and A2 for these two modal damping coefficients. Right? These are called the modal damping coefficients. Why modal? Because each modal equation describes the motion of a vibrational mode. Okay? So that's why it's called modal. And the motivation for the notation A1 and A2, you will see that it would connect you nicely to the theory of scalar second order differential equation. Now here is an important remark. In general, you see, when I concocted, when I fabricated the damping matrix, okay, I intentionally selected the damping coefficient such that when you multiply phi bar transpose times C times phi bar, you would obtain a diagonal matrix. But that is a very special case. In general, you would not have a diagonal damping matrix when you do the multiplication, right? When you do the projection, that's called the projection. Phi bar transpose C times phi bar. Okay, you will not, in general, get a diagonal matrix. And this is an example here. If you select arbitrarily, for example, C1 equal to 1, C2 equal to 3, C3 equal to 2, right? Some seemingly simple numbers, and work out the so then the damping matrix, if you follow the derivation, right? C11 would be the sum of C1 plus C2, C22 would be the sum of C2 plus C3, and C12 would be minus the coefficient small c2. Okay, so that's the same that I have reviewed many times before, and you plug in the numbers. This is the damping matrix, 4 minus 3 minus 3, 5. Right, and then you perform the projection. This is called projection of the matrix C on the basis of the eigenvectors, normalized eigenvectors, okay? Not just regular eigenvectors. And so you see that the end result is not a diagonal matrix. Okay, so damping is a complex, more advanced topic. So this is all I want to mention right now, and please keep that in mind when you go to advanced vibration concept, not the simple single degree freedom. It's not easy. Even if you pick up a book on vibration, mostly the discussion would be on undamped vibration. Okay? Keep that in mind. All right. So the next step is to obtain. Remember the goal. Our goal is to decouple the equation of motions. But remember, the equation of motions involve the displacement, velocity, and acceleration. So you need to say something about the displacement, right? The displacement in the original coordinates led you to a coupled system of equation of motion. Now you want to express the displacement in the new coordinates, and the new coordinates are with respect to the normalized eigenvectors, okay? So here is how you express a vector or a column matrix in terms of the new basis, you know. So these are the normalized eigenvectors, and this is the new displacement, or the components of the displacement in the new basis. Okay, the components of the displacement in the old basis would be d1 and d2, but in the new basis, the notation y is used. So you have y1 and y2, and the notation y is also chosen. Well, I chose the notation y so that it matches the theory of second order, scalar second order differential equation. Okay? Both in the book by Krasik as well as in my lecture notes. Okay? So everything is done with careful thought. Okay, not selected arbitrarily. All right. So this summation here is nothing but that, right? So if you expand the summation, this is what you get. Now, this is the elementary level. Okay, let's say we have only 2 eigenvectors, so you can write like this. But when you have 1 million eigenvectors, or in the case when you solve a system that has 1 million degrees of freedom, but this is much better, right? Because then you can sum from 1 to 1 million in a short, compact formula. If you don't want to expand out with 1 million terms. Okay. So here with 2 terms, right? So you have phi1 bar, y1 plus phi2 bar, y2, and note that y1 and y2 are time dependent, right? So these are the coordinates of the displacement in the basis of the normalized eigenvectors. And you can also rewrite the summation in matrix form in such a way that you bring into the game the matrix cap phi bar, right? Because when you put the 2 normalized eigenvectors side by side, that's cap phi bar. And now you put the new coordinates, or the displacement in the new basis, y1 and y2, as a column matrix that you see, you can write nicely as the matrix cap phi bar times the matrix y. So very good. So this is very important, because this is the y sub I, meaning y1 and y2, has a name in vibration. It's called the modal coordinates. Okay. meaning coordinates of the displacement with respect to the normalized eigenvectors. So here is, let me put on the mask. Recall that we have derived this equation of motion, right? This is the equation of motion written in terms of the matrix variables. Right? You have the mass matrix times the matrix of the acceleration plus the damping matrix times the matrix of the velocity plus the stiffness matrix times the matrix of the displacement d1, d2, right? Equal to the matrix of the applied force. Okay. And so, so now you see you have expressed the displacement in the old coordinates with respect to the new the eigenvectors, right? So the new coordinates are called the modal coordinates. So now you need to, that's the displacement. Now you need to take care of the velocity and the acceleration. So that's just by taking the derivative with respect to time, right? So the matrix of the velocity is just by taking the time derivative of the right-hand side, and you see that only the modal coordinate y sub j is time dependent, whereas the normalized eigenvectors are not time dependent. You know, these are constant. So therefore, the derivative is only on the modal coordinates, and in compact matrix expression, that's the matrix cap phi bar times the matrix of the velocity of the modal coordinates. Right? Y prime.
The velocity matrix is a column matrix, right?
Yeah. So this is 2 by 1. This is 2 by 2. Okay. All right. And so. So then you do the same for the acceleration, right? You just take the second derivative with respect to time, and the second derivative is only carried on the modal coordinates y sub j, right? Because only y sub j with j either 1 or 2 here is time dependent, whereas phi j bar is a constant column matrix.
He said that the velocity matrix it was a column matrix, but it's still scalar, right?
The velocity.
Yeah, it's the
D
same
prime?
as what we just did for regular d time.
Okay, so here d prime. D is d1 and d2, agree?
Yes.
And it's time dependent,
Mm-hmm.
right? So d prime is just d1 prime and d2 prime,
Okay, all right.
right?
Yeah.
And the acceleration d double prime is d1 double prime, d2 double prime. So now y. Y, which is a function of time, this is a matrix. That's y1 and y2.
Gotcha.
Right, so that's the new displacement, or called the modal coordinates.
Modal.
Displacement in the new coordinates of the normalized eigenvectors. Velocity, modal velocity, y prime, right? Then you take the derivative of y and the acceleration, and just second derivative. Okay, yes. So that's the notation. So that's it. So now you can replace. Yeah, let me zoom out now, because now it's okay, let me see whether I can keep everything in. Yeah. So you see the acceleration, you can replace the acceleration by this matrix phi bar y double prime, or in terms of the summation, and that goes here. Okay. Whereas the velocity would be similar to the acceleration, but with the damping matrix, right? You have the normalized eigenvectors, but you have yj prime here. Okay. The summation is just pull out and come on. So for the acceleration, you have mass times the normalized eigenvector phi j bar, and then yj double prime. For the damping force, the damping matrix times phi j bar yj prime. And then for the spring force, stiffness matrix times phi j bar yj. Okay. The summation carried over everything, and on the right hand side, the same force matrix F. Okay. At this stage, let me test the class here. Active learning play. Are these two equations uncoupled? Are these two equations uncoupled?
Yes.
Yeah.
That's the whole point of the modal
Well, yeah,
coordinates,
'cause
right?
Who said yes? Anyone objecting to this? David object?
No.
No. We haven't done anything.
But I thought we just did the
We
phi
haven't-
bar
no,
transpose.
No,
and-
we haven't done anything yet. Because, all we did is just to express the displacement in the new basis.
Okay.
But this matrix here, K here, is still a full matrix. Okay? And in general, C is also a full matrix. You only diagonalize when you pre-multiply by phi bar transpose. That's what we will do next. Okay? Be careful with this. So here, let me zoom out. Yeah, so here, the next step, down here. Okay, you take
Mhm.
phi bar I, because the J had been used as the summation index. So all of these, all of these terms, you have J as the summation index, and now you take phi I bar transpose, okay, multiply throughout, and on the right hand side you also have phi I bar transpose, okay, on both sides. And now you use the orthogonality of the normalized eigenvectors with respect to the mass matrix and with respect to the stiffness matrix, and in this particular case also with respect to the specially selected damping matrix, that this is how you would uncouple the two equations, okay? And that is just, what I just said is right here. You see, you have the orthogonality of the normalized eigenvectors with respect to the mass matrix. And we have seen for the specially selected damping matrix, this is, and for the stiffness matrix, whenever you see the Kronecker delta ij on the right hand side, that means orthogonality, okay? And only when the coefficient is 1, then that means that these eigenvectors have been normalized with respect to the mass matrix, but not with respect to the damping matrix and not with respect to the stiffness matrix. Okay. So let's see what we have with these wonderful expressions. You see, then you can replace phi I bar transpose times the mass matrix by delta ij, phi bar I transpose times C times phi j bar is aj delta ij, and this is phi I bar transpose times k times phi j bar, right? Now what, the magic of the Kronecker delta, remember Kronecker delta, you can think of the Kronecker delta is really like a diagonal matrix already. It's really the identity matrix. Okay. Why? Because this is the sum of j going from 1 to 2, right? But I can think of I equal to 1 now. Let's set I equal to 1. Keep in mind that I equal to 1. First, we think about the case I equal to 2 later. So when I equal to 1, when j equal to 1, then delta 1, 1 is 1. But when j equal to 2, delta 1, 2 are 0. So therefore, the whole equation here would be reduced to only one term. Instead of having two terms, you have only one term. in which I has to be equal to j equal to 1. Okay. So when I equal to 1, then j has to be forced to be equal to 1. Because when j equal to 2, delta ij equal to 0. Delta 1, 2 equal to 0. Okay. So therefore, if you repeat the same argument with I equal to 2, then you get the second equation. With I equal to 1, you get the first equation. Keep in mind, think of I equal to 1. Then you have y1 double prime plus a1 y1 prime plus omega 1 square y1 equal to r1. Okay? That's when I equal to 2. Then you repeat the same argument with I equal to 2. You get the second equation, which is y2 double prime plus a2 y2 prime plus omega 2 square y2 equal to r2. And writing, thank you, Casey. Writing in initial form, basically, just write into one equation.
Can you remind me again what the A is?
Oh, the A here is the modal damping coefficient.
The modal damping coefficient.
Yeah, modal. It's coming from the projection of the damping.
Yeah, from okay. And then that's
Matrix. Yeah.
beta. Alright.
Okay. Yeah. So I think at this stage. Yeah, so here is the B coefficient,
Yep.
and the B is, BI is omega I square, B1 is omega 1 square, B2 is omega 2 square, and you see A and B are the coefficients that you see in the standard second order integration. That's why I chose the B notation, which is the same as B. Okay, so that's the summary.
All we do is wait. What? Like, I like the little dude. So weird. I mean, when I think I got back in the morning, I was see you guys. I don't know if I was back. I don't know if I was going to hide it. I'll see you Yeah, I heard everything. I understand the thing. It's due by Friday.